Subsequently, I would like to introduce the case of cylinder in a uniform flow with circulation. Previously, we have talked about flow over a stationary cylinder, and we have combined uniform flow with a free stream velocity of u infinity to a doublet, and with the help of this I have obtained flow over a stationary cylinder. Now make sure that this doublet is pointed towards the flow. So this case has provided me flow over a stationary cylinder. Now if I go and add my vortex flow in it, then this vortex flow will introduce the circulation effects. Here I have provided the potential and stream function of each elementary flow in polar coordinates. The green is for uniform flow, blue is for doublet, and red is for vortex flow. Now if I want to obtain the scalar potential function for cylinder in a uniform flow with circulation, I will add the potential function of my uniform flow with the doublet and with the vortex flow. Similarly, I can obtain the stream function of this flow by adding the uniform flow, the stream function for doublet, and a stream function for vortex. Now once I have defined the scalar function, I can easily obtain the velocity field for this flow. I can easily determine the location of stagnation points and can easily predict the pressure distribution utilizing the Bernoulli's equation, which I will show you next. Now I will show you the procedure of determining the velocity field. For this purpose, I am selecting the potential function. Here is the potential function for uniform flow over a cylinder with circulation. Now to determine the velocity field, I will go and differentiate this function with respect to r. This will provide me ur component, and with respect to theta will provide me u theta component. And here are the expression for ur and expression for u theta. Now subsequently, I have determined the radius of the cylinder by setting ur0 at the surface. So this is the value of r, and ultimately I have determined the value of k. So the expression for ur and u theta have been written in terms of the radius of the cylinder here. So these are the two expressions for ur, and this is for u theta. Now note that the ur expression is same for a stationary cylinder. However, in the tangential u theta component, this term is showing up due to the effect of circulation. Next, I will determine the location of stagnation points for this flow. To find the location of stagnation point, I have set the velocity component equal to 0. That is, radial and tangential velocities are set equal to 0. Now at every point on the surface of the cylinder, we know that ur is 0, and this has resulted in the value of r equal to capital R, the radius of the cylinder. Now to find the theta, I will utilize the equation for tangential velocity, and I have set this expression equal to 0. Now this has resulted in this expression for theta. So theta is now a function of circulation and radius and free stream velocity. So in this expression, the radius and free stream velocity remain constant. So depending upon the strength of circulation, the location of stagnation point on the surface of the cylinder will change, and we will study those cases in the next. First case, when circulation is set equal to 0, so it means cylinder is not rotating. So it becomes the case of a stationary cylinder. So in that case, only two stagnation points will exist at the front and the rear portion of the cylinder. Now second case, when circulation becomes less than the denominator, there will be a range of stagnation point. So the first stagnation point will lie in third quadrant and second in the fourth. So if I have my cylinder here and I go and divide this from 0 to 90 degree, 180 degree and 270 degree, so first point will lie in this range. Similarly, second point will lie in this range. Third case, when circulation becomes equal to the denominator, so in that case only one stagnation point will exist, and which is here. Now fourth case, when circulation becomes greater than the denominator, so in that case the sine theta value will be larger than 1, which is not possible. So it means that stagnation point will leave the cylinder, and as you can see from this figure. So these are the cases that I have discussed utilizing the equation that I have previously derived for. Subsequently, I have determined the pressure distribution over a rotating cylinder. So for this purpose, I have utilized the Bernoulli's equation, and I have set this equation in this form here. Now remember that we have two velocity component at the surface of the cylinder. So the magnitude of this can be combined using this equation, which is this form here. Now by substituting the value of V square in the pressure equation, in this equation, let's call it equation star, I have obtained the pressure distribution here. Furthermore, I have obtained the coefficient of pressure at the surface of the cylinder by utilizing this equation. So in this equation, I have substituted the velocity magnitude that I have determined previously, and this has resulted me in this form of the Cp, coefficient of pressure. And in this equation, you should appreciate that if I go and set the circulation equal to 0, then I will obtain Cp for flow over a stationary cylinder. So these two terms are modeling the rotational effects on the pressure distribution for a rotating cylinder.